oscillations. Yesterday, in the last lecture, we have considered the various methods which are available to solve the numerical boundary eigenvalue problem posed by considering or by the description of radial and non-radial linear pulsations. We have discussed various methods, and we have finally considered the so-called Riccati method, which is a shooting method. A shooting method means the perturbation problem or the differential equation is considered as an initial value problem, integrating from the boundaries towards the center of the integration interval, which has, in the case of a boundary value problem, the disadvantage that you have only part of the boundary conditions given, and the other part of the boundary conditions needs to be guessed and needs to be iterated. So there are in general, no unique boundary conditions no unique initial conditions for the integration of a shooting method from the boundaries. And this causes also not only the problem that these missing boundary conditions have to be iterated, but it also introduces in general for systems which are higher than second order, it causes numerical instability, in particular the parasitic growth problem, which makes them not suitable or makes them not applicable for higher order systems. Well, a solution of the problem is the so-called Riccati method. It is a shooting method which integrates from the boundaries towards the center of the integration interval with unique and unambiguous initial conditions. We have then convinced ourselves that our systems, the radial and the non-radial boundary eigenvalue problem, can be used or can be written in terms of the Riccati formalism, and we can apply the Riccati formalism to our problem. Okay, we ended up with the Riccati. We convinced ourselves that, for instance, the matrices contained in the Riccati formalism are maybe filled according to our needs with our coefficients, which are given by the perturbation problem we have derived, and in particular that the boundary value of the Riccati matrix is given in a unique way by the boundary conditions of the system. So the Riccati matrix has unambiguous values at both boundaries. There are no degrees of freedom, and we can use these unambiguously defined values of the Riccati matrix as unique initial conditions for the integration of the Riccati equation, which is a matrix differential equation which is no longer linear but which contains a nonlinear term. Okay, so we have overcome the ambiguity in the initial conditions. We have unique initial conditions, and we can now integrate the Riccati equation as an well-defined, unambiguous initial value problem from each of the boundaries towards the center of the integration interval. Okay, so if it is not possible to formulate the boundary condition within the framework or according to the definition of the Riccati matrix, we may also take the inverse of the Riccati equation of the Riccati matrix as a dependent variable, and we end up with a similar equation, with a similar Riccati type equation, simply by exchanging the role of the matrices A's and D's and B and C. So we can alternatively define V is S times U, and S In the case if S has an inverse, then S is given by the inverse of the Riccati matrix. And we obtain a similar or the same equation simply for S, simply by exchanging the matrices A and D and the matrices B and C. Okay, this is the strategy, and the question is now, how do we determine then the eigenfrequency sigma? The matrices A, B, C, D contain information about our stellar model, our hydrostatic stellar model, and they contain the parameters sigma, the eigenfrequency, and if we consider non-radial perturbations, then it also contains the parameter L, which is the harmonic degree. Okay, so let's start the integration both at x equal to 0 and x equal to 1, taking, for this example, taking the relative radius as the independent variable, but you can also take it as an example for any boundary value, in terms of the independent variable x. So we have two boundaries here at x equal to 0 and at x equal to 1. Our boundary conditions give us a unique and unambiguous value for the Riccati matrix, both at the inner boundary and at the outer boundary. So this R is given by R in 0 and R out 0. And we can start with these initial conditions to integrate the Riccati equation. We perform the integration to some value of the independent variable, which we call the x fit. This is a in principle freely chosen value to which we integrate our matrices R by integration of Riccati equation, and what we obtain is the final value from the integration from the inside. We obtain the matrix R in at the point x fit, and the integration from the outer boundary towards x fit yields the matrix R out at x fit. Okay, so we can freely choose this fit point. This might be important to determine afterwards, or might be this point can be chosen such as that the subsequent iteration can be done in a convenient way. So we are free to choose this fit point in the middle of the integration interval. Okay, how do we determine now the eigenfrequency sigma? Well, at x fit we require that the functions u and v, which we don't integrate, we don't know the functions u and v, we only know the Riccati matrix R. So we require that our functions u and v are continuous at the fit point. This is necessary because they have to satisfy a differential equation. They have to be differentiable. That means they have to be at least continuous at the fit point. Okay, this means that the integration, or well, we haven't done the integration of u and v, but suppose we did the integration of u and v from inside and outside, then of course the value of the integration of the component u from the inside has to be equal to that from the outside, and similarly also the value of the component v integrated from the inner boundary has to be equal to the value of the integration of v from the outer boundary. Okay, now we know by definition that u in is given by Riccati matrix integrated from the inside times v in, and this has to be, by this requirement, has to be equal to u out, which is given by definition by R out times V out. Now V out has to be, by the continuity condition, has to be R out times V in. That means if we compare these two terms, this term and this term. That means R in minus R out acting on V in is 0. This homogeneous linear equation only has a solution if the determinant of the matrix R in minus R out is 0. So we get as a condition for the solution, necessary for the solution, for the continuity of the variables at the fit point, that the determinant of the matrix, the Riccati matrix, obtained from the inner integration minus the Riccati matrix obtained from the outer integration has to be 0. Okay, well, Riccati matrix is a complex matrix, so this is a complex function of a complex variable. The only variable we have left in our system is the complex variable. Sigma is the complex eigenfrequency. So we are left with a simple, with one equation only, one equation, one numerically given equation. It's a complex equation of a complex variable whose zeros determine the solutions for the eigenfrequency sigma. So this equation can be used to determine now the eigenfrequency sigma. There is no ambiguity in the initial conditions. The only ambiguity or the only parameter of this integration is the eigenfrequency, and in the end we obtain a complex function whose zero are the eigenfrequencies sigma. And it's gratifying that this procedure, this numerical strategy is in fact stable. Okay, so we have a function whose zeros is here, whose zeros determines the eigenfrequency. We did not need any information or any estimate for the solution. Nothing is required. The initial conditions are unambiguously defined. The coefficients of our matrices, the boundary conditions, are unambiguously defined. There is no information and no estimate on the solution, for instance, on the eigenfunctions, is required. Nothing. We just integrate the full system of equations. We don't need to have an approximation to the system. We don't need to solve an approximate problem to get an estimate for the eigenfrequency. We take the full system of equations and get finally a simple one-valued complex function whose zeros are the eigenfrequencies. So if we want to get an overview where the eigenfrequencies are, we simply have to integrate the Riccati equation for various values of the eigenfrequency over the complex plane, and we have to tabulate the determinant function. Okay, so example, to get an overview where the eigenfrequencies really are. Well, we take, for instance, we could also go over the entire complex plane and tabulate the determinant function over the entire complex plane. For practical purposes, it's easier to go along some lines. Here we have taken a line parallel to the real axis, so we have a constant imaginary value, and we tabulate the function along this dashed line parallel to the real axis. But you could also take a line going at a certain slope through the complex plane. You are free to obtain an overview over the run of the determinant function in any other way. You could also cover the entire domain of the complex plane with tabulating the determinant function there. So it's a complex valued function of a complex variable given in terms of sigma r and sigma I. These are the quantities which we want to know. as an example how this might look like is the modulus, the log of the modulus of the determinant is given along such a cut through the complex plane. And what we see here, we see pronounced minima in the determinant function here, there, and there. And these are the places which seem to be close to a real root of the determinant function. So if we take, for instance, these values as an initial value for the iteration, for the subsequent iteration, we might end up here with the eigen frequencies which we were looking for. So the first overview over the run of the determinant function can be obtained by simply taking a cut through the complex plane and then tabulating the determinant function here. These dots, each of these dots corresponds to one integration and gives a certain value of the determinant function. And whenever the determinant function vanishes, we have an eigenfrequency of the system. So no iteration of any other parameter has to be done. The only iteration which is needed then in the end is to determine precisely the value of the eigenfrequency once we start from an estimate of the eigenfrequency obtained, for instance, by tabulating this function without any reference to any approximation or any auxiliary solving an auxiliary problem. This can be done for the full system of the equations. Okay, so for the precise determination, the determinant function itself may provide reasonable initial conditions or reasonable initial guesses. Questions? Everything is clear? Okay, now I have to comment on some problems here. The Riccati matrix may become singular during integration, so it may diverge. This is not a numerical error. This is a genuine property of the Riccati equation. If that happens, that means if the determinant oversteps some critical value, becomes bigger than a given value, then we can switch to the inverse. So we stop the integration of the Riccati matrix, we determine the inverse of the matrix, and we integrate further on the inverse of the Riccati matrix. It's also a Riccati equation with the matrices A and D and B and C interchanged, and then we integrate the inverse until possibly also the inverse of the matrix becomes singular, and we switch then back to the integration of the Riccati equation. So this is not really a problem, but it requires in the program, in the code, it requires the possibility to switch from the Riccati matrix to its inverse and back. If needed, if we meet a singularity, we can overcome this problem simply by switching to the inverse once the determinant has reached a certain value, and above this value we will integrate the inverse of the matrix. So this is some additional strategy which has to be taken into account. Now you may want to know whether we also can determine the eigenfunctions. So far we have only determined the eigenfrequency, and we have a Riccati matrix which has not, on first sight, which has not much to do with the eigenfunctions. So what we are interested in are also the eigenfunctions u and v. How can we get the eigenfunctions u and v in this Riccati method? Well, we determine, first of all, we determine the eigenfrequency, and we determine the Riccati matrix as a function of the independent variable. So we have to iterate and determine the eigenvalue, and once we have found the eigenvalue, then we integrate the Riccati matrix with this eigenfrequency and determine and store it at certain points in the integration interval. So we determine the function Riccati matrix as a function of the independent variable in the integration interval. Now at the fit point we know that the difference of the Riccati matrix from inside and outside acting on the component V of x fit has to be 0. We know that there is a solution to this equation because the determinant of R in minus R out was required to be 0 to have a solution. So we may calculate V at x fit at the fit point. So this has a solution, a non-trivial solution, and therefore the determinant of the difference of the two matrices is 0. That means V of x fit has a solution. Well, I have to remind you, this is just a 2 by 2 matrix, so this can be done by hand to determine the solution of V of x fit, because in the case of radial perturbations, the Riccati matrix is a 2 by 2 complex matrix, and for the non-radial problem, Riccati matrix is a 3 by 3 matrix. So these calculations can be done by hand. These are not big matrices, but small matrices. Okay, so we have a solution, or we have the value of V at the fit point. What we do now, we solve the equation for V. V is given by U and V and the matrices C and D. We know the matrices C and D, and this is the differential equation, so it's the second half of our original system. V dash is given by C times U plus D times V. U may be written as R times V, and we know from the integration, from the first step, we know the matrix R, so we do know the matrix C, R, D, and this is an equation with coefficients which are known and are predetermined, and this is our linear equation in the part of the variables V. So this is in the radial case, this is a second order system of equations here with known coefficients, and we have a known initial condition at the fit point. So what we do, we integrate this equation from the fit point back to the boundaries. So Riccati matrix, let's say following, here is x equal to 0 and here is x equal to 1. So the Riccati matrix is integrated from the boundaries to the fit point, x fit, and this is the Riccati integration. Now we are starting, for the integration of this equation, we are starting with unique initial conditions at x fit, and we go back here with the V integration towards the boundary, because we have the unambiguous initial conditions here. Okay, so we have determined, once we have integrated this equation, we need to do this only once. Well, then we know also the Riccati matrix, we know V in the entire integration interval, we know the Riccati matrix, and so by U is equal to Riccati matrix times V, we also have the component U. Okay? So the important thing is that we need to specify, for this integration, we need to specify the Riccati matrix from the beginning. We cannot integrate the Riccati equation simultaneously with this equation, because that would again become numerically unstable. So what we have to do, we have consecutively, we have to determine first the eigenfrequency, the Riccati matrix, and then with the known Riccati matrix we have to integrate the V component back to the boundaries, and then with the V component and the known Riccati matrix we have both U and V. So that's the way how to determine the eigenfunctions in the Riccati method. Okay, finally we have U is equal to R times V, and we have completed the determination of the eigenfunctions. So we do not only get a stable procedure to calculate the eigenfrequencies, we can also determine the eigenfunctions. So we have everything. Okay? Well, the Riccati method is very reliable because you can determine the final result of the Riccati method is a complex functions whose zeros are the eigenfrequencies. You can consider, or you can investigate the surrounding of a zero, and therefore you can check whether your eigenfrequency is a numerical artifact or whether it's a physical eigenfrequency. You always have control over the determination of your eigenfrequency. So it's pretty reliable, and you can always at each step you can check whether your numerical procedure works or gives you fake results, or whether the results are physically meaningful. The second advantage of the Riccati method is that you can achieve an extremely high accuracy because it's a shooting method, and the accuracy of the integration can be controlled locally to meet any prescribed accuracy for the integration, and also of the iteration of the eigenfrequency in the end can then be done with predefined accuracies. So the method is particularly well designed for eigenvalue problems which require a high accuracy. And I would have liked to show you one of the most demanding eigenvalues problems we have encountered. This is taken from fluid mechanics, and it's a very basic problem in fluid mechanics. It's the stability of the so-called Poiseuille flow. Poiseuille flow is the flow through a pipe, or in an idealized case, it's the flow between two planes, which is generated by a pressure gradient. Either you have a very simple configuration. You have a pipe and you have a pressure gradient. You have a higher pressure on top than on the bottom, and then the flow will be initiated through the pipe, and it will have a parabolic profile. This flow does not stay a laminar flow. It does not stay this. It does not continue with a parabolic profile, but it becomes turbulent. And the big question in fluid mechanics is, when does this flow become turbulent? And for this reason, we do a stability analysis, and we consider, or we investigate, the stability of this flow. Now, this is a very simple problem, and the stability problem and the question, when does this flow become unstable, what is the typical Reynolds number when this flow becomes unstable, is a very old problem. It was posed the first time by Orr and Sommerfeld in the end of the 19th century. So the problem is more than 100 years old, but it took almost 80 years to solve the stability problem and to tell people what is the Reynolds number above which this flow becomes unstable. So it is very hard, it's an extremely hard boundary eigenvalue problem of fourth order, very similar to our stellar pulsation problems. This is also fourth order. So this stability problem leads to a fourth order boundary eigenvalue problems, very similar to that which we consider in the framework of astrophysics. So 80 years, only in the 1970s, the first reliable numerical calculations have been done to determine the critical Reynolds number for this flow. I would have liked to show you that you can do it actually with the Riccati method with not very much effort. You don't need big matrices, nothing. You take the Riccati method, you put in this fourth order equation in the same way as we do it for the radial and the non-radial perturbations, and we get extremely accurate results comparable to the latest results which were obtained using Chebyshev approximations and so on. Very sophisticated mathematics was applied to determine this critical Reynolds number. If you plug it in your Riccati formalism, you immediately get the highly accurate results. I will not have the time to show this to you. If you are interested, the rest of the transparencies contains this example for treatment of stability, highly demanding stability problem with the Riccati method. Okay, but one thing I want to mention with this is, where does this singular solution of the Riccati method come from? Since we had to switch from the Riccati matrix to its inverse here, but what is the reason for the singularities of the Riccati equation, or the solutions of the Riccati equations to occur? Okay, let's consider a very simple equation which we can represent, or which we can write as a Riccati equation. Let's consider the harmonic oscillator. The second derivative of u is given by minus kx. This is the equation for the harmonic oscillator. You know the solution. What is the solution of the harmonic oscillator? What do you see? It's an oscillator, so sine and cosine is the solution of this equation. So a second order equation, and we may rewrite it in terms of a first order, of a system of first order. So we write u dash is equal to v. We introduce a new variable, then v dash, this is the second derivative, is given by minus ku. Well, we have already taken the right notation. We have taken u and v. So this is maybe written as u dash is equal to a times u plus b times v, and v dash may be written as c times u plus d times v. This is the first step in a Riccati treatment. A is now not a it's a 1-by-1 matrix rather than a 2-by-2 matrix in the case of a fourth order system. And we read off from the comparison of these two equations that B is equal to 1, it's V, C is minus K, A and D are 0. So our famous harmonic oscillator may be written in terms of a Riccati equation, and we can explicitly write down the Riccati equation here. So we know that R dash is equal to B plus AR minus RD minus RCR. A and D are 0, B is 1, so this is 1 minus K R squared. This is a nonlinear equation with regular coefficients. Well, and we know the solution of the original equation, the second derivative of u is minus kx, so we have cosine square root of k and sine square root of k as a solution of the equation. So we know that u and v are given by cosine and sine alpha t, where alpha is square root of k. So u, the most general solution for the harmonic oscillator, is c1 cosine squared k times t plus c2 times sine square root k of t. V is the derivative of u, so v is u dashed, this is square root of k. We simply differentiate the cosine and sine, and we get the sine and cosine instead here. Okay, now we know the Riccati variable, so to say the solution of this equation, the solution of this nonlinear equation, which is simply the Riccati matrix is simply the ratio of u and v in this case. R is u over v, and we know u and v here. So we are left with the Riccati variable is given by, in the nominator, the cosine and sine term, and in the denominator we have minus sine and cosine. Well, this function here can have zeros. So we have singularities if we choose square root of k and the integration constants appropriately, then the denominator will have zeros, and we will have singularities which are not caused by some numerical effect. This is simply because the solution of the Riccati equation has singular solutions. That's a little bit surprising. We have a well-behaved equation, the Riccati equation. The coefficients of the Riccati equations do not have any singularity, nor do the initial conditions have any singularities or so. The only point is that this equation is nonlinear, is a nonlinear equation, and this produces, for the solutions, it produces singularities, and these are genuine singularities. They cannot be removed by any trick or any numerics. If we want to calculate this numerically and we are not aware of these singularities, then we will make big errors if we just cross these singularities, because we cannot handle singularities numerically, but the solution of this equation has genuine singularities. We have to be aware of these singularities. What we do, we switch in our approach, we switch to the inverse, which then of course has a zero, so we can integrate it simply by switching from the Riccati variable to its inverse. That's where the singularities come from. They are not some mathematical or numerical artifacts. They are genuine singularities of the nonlinear equation. For a linear equation with regular coefficients, we would never get such a behavior. Linear equations, once they are well behaved, once they have no singular points, or if the coefficients remain regular and finite, we will always have finite solutions. This is not true for a nonlinear equation. Okay, that's just to demonstrate how these singularities are introduced here in the Riccati formalism. Okay, now if you are interested in this stability problem, well, I'm afraid that we will run out of time. Once we have some time left, I will come back to this and I will explain you in detail the solution of the Orr-Sommerfeld equation using the Riccati method, and at the same time solving the stability problem of the pipe flow or the plane and circular Poiseuille flow. Let me just show you this is the problem. Well, we have a pressure P1 and P2, and this pressure causes the fluid to flow between these two boundaries. It has a parabolic profile, and once you increase the pressure over a certain threshold, or in other words, if the flow speed becomes too high, then this flow becomes unstable. It switches to turbulence, switches to become turbulent, and the onset of turbulence is the problem we want to solve. We want to know when does this flow become unstable? What is the typical Reynolds number above which we have turbulence for that flow? The Reynolds number is of the order of 5,000, and you can determine this using the Riccati method very precisely to 5,772 point something. Okay, so the Riccati method can be used to determine this very demanding, long-standing problem of fluid mechanics. Okay, so let's now close this session about the numerics of the linear stability problem, and let's come to another topic which we have already touched a little bit. So this is then the next file on the adiabatic approximation. Okay, we have in one of yesterday's lectures, we have considered, or we have discussed the coefficient C1, which appears in the perturbation equations. The coefficient C1s we have seen is essentially the ratio, or denotes essentially the ratio of the thermal timescale to the dynamical timescale within the star, and the coefficient is, apart from being large in the center, it also diverges in the center, and this requires an irregularity condition which is identical with the requirement that the changes of state have to be adiabatic. So the boundary condition at the very center of the star, the regularity requires adiabatic changes of state. And even if we get close to the boundary, to the inner boundary, this coefficient C1 becomes very large because thermal timescale becomes big, and this means thermal timescale becoming large means that a mass element cannot exchange heat with its surroundings, and therefore its entropy has to be constant, or the equations of the changes of state have to proceed adiabatically. Well, now we saw that for the ratio of thermal and dynamical timescale becomes smaller if we approach the surface of the star, but this is different for different stellar models. You have different behavior, so we consider the Cepheid and the hydrogen deficient carbon star. So in this part of the star where the ratio of thermal timescale to dynamical timescale is big, we have this forces us to have adiabatic changes of state. This is no longer true if you go close to the surface. Now, for the Cepheid, the domain where we have small thermal timescale is small compared to the domain where the thermal timescale is big. This is not true to the same degree for a hydrogen deficient carbon star. In the inner part, again, thermal timescales are large. In the outer part, or in a larger fraction of the outer part, the thermal timescales are small. But for those stars where this region of low thermal timescales is small, we may try to apply the adiabatic approximation, or we may apply or assume adiabatic changes of state for the entire star. Of course, for the inner part, it will be okay. It's justified. But the question is, do we also get a reasonable approximation to the problem if the domain or the region where thermal timescales are small are negligible or small in our star? This might be the case, or we might think that this could be the case for a Cepheid. It's certainly not true for a hydrogen deficient carbon star. Or if we compare the other two stars, for the 60 solar mass star, the domain where the thermal timescale to dynamical timescale falls below unity is only a few percent in the star. It's only at most at the outermost 10%, whereas for the 24 solar mass, it is almost half of the star, where the timescale, the thermal timescale, is smaller than the dynamical timescale. Okay, so for the 60 solar mass star, we may try to apply the adiabatic approximation all over the star, and we could then compare the results of the full non-adiabatic analysis with the result of the adiabatic analysis. Okay, that has been done already yesterday, and so we can start off from the results of yesterday's lecture. Well, the consequence of requiring adiabatic changes of state, or the Lagrangian perturbation of entropy to vanish, is that the equation of state, which might be formulated either in terms of the pressure as a function of entropy and temperature, or the pressure as a function of pressure of entropy and density, then reduces for s equal constants to p as a function of t, or p as a function of rho. And once we differentiate it and go to the Lagrangian perturbation of pressure and pressure, density and temperature, we end up either with delta p is proportional to nabla adiabatic in the case of delta t, or being proportional to gamma adiabatic times the relative change of density or temperature respectively. Or in terms of relative changes, which are used in the perturbation equation, that the relative change of temperature is given by nabla adiabatic times p. That has been discussed already yesterday, and we also saw that in this case the thermal and the mechanical equations decouple and only the mechanics remains left. That's the result of yesterday. We have a reduction in the order of the differential system. We end up with a second order system, and only sigma squared appears in the equation. Apart from sigma squared, all coefficients are real. There is no complex coefficient left. Well, the sigma squared is the term which is associated with the mechanical acceleration. Okay, that has been seen yesterday. Well, we require for validity, as discussed yesterday and just a few minutes before, that adiabatic approximation is always valid in the stellar interior. Deviations from adiabaticity are only found in the outer envelope, and whether the adiabatic approximation is satisfactory or is expected to be satisfactory depends on this particular stellar model. Cepheid seems to be well suited for the adiabatic approximation. Hydrogen deficient carbon star does not seem that suitable for the adiabatic approximation. Okay, so we are left with, in the end, with the equations we have already discussed. These are okay, we are left with the following equations. Well, these were the equations we were left yesterday. This is the mass conservation equation. This is the momentum conservation equation, and we have two boundary conditions: the remaining regularity condition at the center and the force-free boundary condition at the surface. Okay, this is the system which we are left in the adiabatic approximation. Now I have to go back a little bit, and I have to quote a theorem, a famous theorem. The adiabatic perturbation problem is, both for radial and non-radial perturbation, is self-adjoint. Self-adjoint means that the eigen frequencies or the eigenvalues are real here, meaning that sigma squared is real. So without proof, the adiabatic perturbation problem is a self-adjoint problem, with the consequence that sigma squared taking sigma squared as the eigenvalue, sigma squared is real. We will see this explicitly for the radial case later on. We will automatically end up with a proof for self-adjointness and real sigma squared, whereas the proof for the non-radial perturbation is somewhat more involved, and I don't want to get through all the algebra and the mathematics to prove that even the non-radial problem, the non-radial adiabatic problem, is self-adjoint and and leads to real values of sigma squared. Now, what does this mean for our system? So sigma squared is real, and then we can decide or can distinguish between positive and negative values of sigma squared. If sigma squared is positive, the root of sigma squared is real, and we have plus minus sigma r, real part of the eigenfrequency. That means we have an oscillatory, neutrally stable situation. Sigma I is 0 in that case. The other case is if sigma squared is smaller than 0, then the solution of this equation is imaginary, so the solutions will be plus minus I sigma I. We have no oscillation, sigma r is 0. We have a non-oscillatory instability and damping at the same time, because note that the negative values of sigma I mean excitation or instability, and positive value means damping. So we have always a pair of unstable and damped modes. They come always in pairs of a stable and an unstable mode, and they are non-oscillatory, so they don't oscillate. So we have in that case an unstable and a damped, exponentially growing or decaying mode. Both come at the same time. So either if the star is to be stable, then it has to be neutrally stable. No, the sigma I is 0. It only has a frequency, and the amplitude of the pulsation or of the oscillation will not change. Neutrally stable, no change in the amplitude, or if it is unstable, it has a damped counterpart, and it is a non-oscillatory instability. Okay, adiabatic instability is always exponential, non-oscillatory, and occurs once the sigma squared, once the square of the eigenfrequency becomes negative. Sigma squared has to stay neutral, has to stay real quantity. Okay, so now this is what we get from our consideration, from considering the adiabatic limit of the non-adiabatic system. Well, this is not the conventional, not the standard form of the perturbation equation which is usually used. In order to end up with a standard equation for radial adiabatic perturbations, we have to transform this system. We have to transform it into a single differential equation of second order. We have to transform the independent variables back from log P naught to the radius, and well, okay, the first step would then be to transform the independent variable. So far we have log P naught as the independent variable, and the transformation from P naught to R can be done using the definition of our coefficient C4, or by applying the hydrostatic equilibrium. D log P naught by d log R is nothing but the pressure gradient in the equilibrium between gravity and pressure gradient. So we have d log P naught over d log R is minus 1 over C4, and this is given explicitly by density, pressure, and the gravitational potential energy. So the derivatives with respect to log P naught, which are contained in the above equations, can be rewritten d in terms of the derivative with respect to r by d log P naught is minus c4 times r times d by dr. Okay, we do this transformation, then we eliminate the pressure perturbation and we keep the Lagrangian displacement. So we try to get rid of the pressure, and we express our perturbation problem only in terms of the Lagrangian displacement, obtaining a second order for equation for the Lagrangian displacement. Okay, so now of course we also have to insert the definitions of C3 and C4, and after some algebra, if we do that, after some algebra, we are left with the following standard form of the radial adiabatic wave equation. Okay, I don't want to go through all the algebra and all the mathematics. If you're interested, you can try with these instructions, you can try to arrive at this equation doing after some algebra. Okay, this equation is of second order. There are two derivatives with respect to the radius of the Lagrangian displacement, and this differential operator is a differentiation onto a term which contains first some quantities of the background model, which is the adiabatic index, the pressure, and the radius to the fourth, and this acts on the this function times the derivative of the Lagrangian displacement has to be differentiated. So this is the differential operator which is contained in the final equation, plus zeta times a bracketed term which contains in the first place the sigma squared and some function including the density stratification and the radius, and the second function containing the pressure stratification and the adiabatic index. We see that the function f and g, this is denoted by function f, is bigger than 0, and also the function g is bigger than 0. So this is the standard form of the radial adiabatic perturbation equation, second order perturbation equation. Of course, we have to transform also the boundary conditions. At the outer radius, at the surface of the star, we have that the pressure perturbation has to be 0. In terms of the Lagrangian displacement, this condition can be rewritten as r times d zeta by dr plus 3 zeta is equal to 0. And at the center, again, we have a regularity condition. You see, for instance, at the center, this coefficient will vanish. So this is a singular point, and this requires a regularity condition also for this equation. Okay, now how shall we proceed further? Well, first of all, the physically relevant quantities which enter this equation is the density stratification. If we look here, that's the density stratification, the pressure stratification, and as an important additional quantity, the adiabatic index. This means one of these indices coming from thermodynamics, denoting the d log p by d log rho at constant entropy. These are the three quantities which determine or which are essential for the radial adiabatic perturbation problem. Now we identify the Lagrangian displacement with y, and we identify our eigenfrequency squared, sigma squared, with lambda. Then we can write this equation in a form which is very well known in mathematical physics. This is a so-called Sturm-Liouville equation. Well, the derivative of f times the derivative of y dash That is simply the first term of the adiabatic wave equation. So the derivative of f times the derivative of zeta, this is the first term, plus y times, y denotes the zeta, times the eigenfrequency, this is sigma squared, times the positive function g plus a function h is equal to 0, with the condition that f and g has to be a positive function. So this is a Sturm-Liouville equation, and this has been thoroughly discussed by many mathematicians in the end of the 19th century and in the 20th century. And we can take any of the properties of this Sturm-Liouville problem and transfer these properties to our linear adiabatic wave equation. Well, let's first of all study the property of the differential operator. We will come to the general properties of Sturm-Liouville equation later, but some of the properties we should convince ourselves in detail. So what we do, we take the operator, the differential operator occurring in the linear adiabatic wave equation, that is d by dr gamma adiabatic p naught times r to the fourth, acting now on a function on a Lagrangian displacement which we denote by zeta 1. We multiply this differential operator acting on zeta 1 with the function zeta 2 and integrate the entire quantity over the integration interval, that means from 0 to the surface. Now we perform a partial integration by putting this derivative onto the zeta 2. Then we have boundary term, which is zeta 2 times this factor times d zeta 1 by dr. This has to be evaluated between 0 and r. Now at the radius r, p naught is 0 or close to 0, and at r equal to 0, the term r to the fourth is 0. So this boundary term vanishes, and we are left with minus. The derivative is now put to the zeta 2, is d zeta 2 times the function gamma p times r to the fourth times d zeta 1 by dr. Now we again perform a partial integration and put this derivative onto the rest of the integrand. Then we get again a boundary term. The boundary term now looks like minus d zeta 2 by dr gamma adiabatic p r to the fourth times zeta between 0 and r, and again at the outer boundary pressure vanishes, at the inner boundary the r to the fourth vanishes. That means the boundary term vanishes again, and we are left now with the rest of it. This is d by dr. So this derivative has been put on this term. So we are left with zeta 1 and the derivative of d zeta 2 by dr gamma adiabatic p naught r to the fourth with the sign changed. So what we get at the end is the final result is the integral over zeta 2 with a differential operator acting on zeta 1 is equal to zeta 1 and the differential operator acting on zeta 2. So this operator is said to be symmetric, or in mathematical more elegant way, it's a self-adjoint operator. What does it mean? If this differential operator is symmetric or self-adjoint, well, let's abbreviate this differential operator with d acting on zeta, and let's consider the following integral. So we take the integral of zeta star. Star should denote the complex conjugate. So we multiply the operator d or acting on zeta with the complex conjugate of the function zeta, integrate over the interval and take the complex conjugate of this quantity. Well, the operator d is real, and the only complex quantity appearing under this integral are the eigenfunction or are the functions zeta. So taking the complex conjugate, this will give the original value complex zeta twice complex conjugated gives the zeta itself times d acting on zeta star. Well, because this operator is found to be symmetric, this is equal to zeta star times d times zeta, and this means if we compare this quantity with that one, well, the complex conjugate of this quantity is equal to the quantity itself. What does it mean? It's a real quantity. So this integral is real. Well, if we now consider the complete equation, we multiply the equation, the linear adiabatic wave equation, with a complex conjugate of zeta and integrate over the volume, then we are left with zeta integral over zeta star d acting on zeta plus sigma squared integral over the function g zeta star times zeta plus integral over the function r zeta star times zeta dr is 0. This is simply integrating, multiplying the equation with the function zeta and integrating over the volume or over the integration interval. Then we know, well, this quantity we know is real. Well, zeta star times zeta is the modulus of zeta squared. So this is a real quantity, g is real, and all the same is true for h, and zeta star times zeta. So this is real, that is real. So sigma squared has to be real. That's what we have proven explicitly now for the radial system, that the differential operator is self-adjoint and sigma squared therefore is real. So we have proven self-adjointness and reality of the eigenfrequency sigma, or of the eigenvalue sigma squared. Okay, that means sigma squared, we have explicitly shown eigenvalues sigma squared are real. And that's what we have used before to show that instabilities in adiabatic regime are exponential, and if a star is to be stable, it has to have neutrally stable oscillatory mode. Instabilities are never oscillatory, they are exponential, and also come with a damped counterpart. Okay, shall we make a break here? And after the break, we will show some other properties of the linear adiabatic system, linear radial linear adiabatic system. Okay, we were about to consider and to investigate the properties of the linear adiabatic wave equations, adiabatic wave equation. One point we have found was that the linear adiabatic wave equation is a Sturm-Liouville type equation, and we can take all, or can adapt all the properties of the Sturm-Liouville problem and make use of it for the adiabatic wave equation. Well, one of the most important properties is that the operator, the differential operator, is self-adjoint, and therefore the frequency sigma squared, not the frequencies themselves, but the frequency sigma squared have to be real, and we have explicitly proven it by considering the properties of the differential operator. There is another property which I would like to comment on in detail. This is once we consider two functions zeta m and zeta l, which are supposed to be eigenfunctions for two different eigenvalues, sigma m squared and sigma l squared, then we have, according to the perturbation equation, that sigma m squared times the function g acting on the function, the eigenfunction zeta m, is differential operator acting on zeta m minus h times zeta m, and we consider the second eigenfunctions zeta l, or sigma l squared. So we have the equation for sigma l squared times g acting on zeta l is equal to the differential operator acting on zeta l minus h acting on zeta l. For convenience, we take the complex conjugate of the second equation. Complex conjugate means all these quantities are real, so only the complex conjugate of the eigenfunction is to be applied here. Operator d is real and h is also real. What we do now is we integrate the first equation with the second eigenfunction zeta l star, and integrate the second equation with the first eigenfunction zeta m, and integrate over the integration interval. Then we are left with zeta m squared times the integral over g times the product zeta l star times zeta m, and down in the second equation we have zeta l star times zeta m. Then we have the term containing the differential operator zeta l star times d zeta m, and in the second zeta m times d zeta l star minus h times zeta l, where is it? L star is the product here, times zeta m, and of course down the second one is zeta m times zeta l star. Okay, now we know that these two terms are the same because the operator d is symmetric, so we can interchange zeta l star and zeta m, and we can subtract these two equations. Okay, then these two terms will cancel because the operator is symmetric, and these two terms will cancel because of obviously zeta l star is equal to zeta times zeta m is equal to zeta m times zeta l star. So the difference of the right hand side is 0. Main argument is that the operator, the differential operator, is symmetric. Okay, what are we left with? We are left with then, of course, this product zeta l star times zeta m and zeta m times zeta l star is the same. So these two integrals are identical, and we have sigma m squared minus sigma l squared times the integral over the function g times zeta l star times zeta m has to be 0. What does it mean? Well, if m is not equal to l, then this bracket is non-zero. Then obviously this integral has to vanish. That means the integral over G times zeta L star times zeta M is 0 once we do not have the same eigenfrequency. Sigma M is not equal to sigma L. If M is equal to L, of course, then we have that. Then we have the following integral. Then we have G integral over G times zeta M star times zeta M, which is the modulus of zeta M squared, zeta M squared. Of course, this quantity is real, and this condition or this reality may be used for the normalization of our eigenfunctions, normalization such that this integral is unity. This means normalization. Okay, so we can normalize our eigenfunctions in a way that the integral over the function g times the modulus of the eigenfunction squared is unity. What does this mean? Well, this means normalization of the eigenfunction, and this condition, if we have two different eigenfrequencies and we consider the integral over the product of two eigenfunctions which do not belong to the same eigenvalue, what does it mean? If you remember possibly quantum mechanics, in quantum mechanics you have similar problems. How do you call it? The eigenfunctions are orthogonal. So their product or the integral over their product is 0. So the eigenfunctions of our linear adiabatic wave equations, they form an orthogonal system, and if you normalize it, then you have a so-called orthonormal system. This means you can expand any function depending on radius in terms of these eigenfunctions of the adiabatic wave equation. Well, we haven't proven, and this is a little bit more difficult, that it's a complete orthogonal system or orthonormal system, which means that any function can be represented as an infinite sum over the eigenfunctions of the problem. This might be this property is sometimes used if we go to astro and helioseismology. Then you can expand your functions you want to represent in terms of the eigenfunctions of the adiabatic stability problem, either on the radial or the non-radial problem. So this is an important problem, important property, which might be used later on in helio and astroseismology. The eigenfunctions form an orthonormal system, here explicitly shown for the case of radial adiabatic perturbations. Okay. Well, now I would like to comment on some additional properties of the linear adiabatic wave equation for radial perturbations, but without proof. I will resort now to the standard results known from the mathematical studies of Sturm Liouville systems. So there are many theorems about Sturm Liouville systems. To remind you again, Sturm Liouville systems are typically of the form or are defined by an equation, a differential equation of this form, and we have seen that our problem is exactly of this form with the property that f and g are positive functions. So the results, we can take the results which are known from the mathematics of this system and apply it to our linear radial wave equation. Okay, so what are the main results? There are many results, but I will refer only to those which are interesting to us. Okay, the first theorem states there are infinitely many real non-degenerate eigenvalue is lambda. Lambda is now the equivalent of sigma squared, with a smallest eigenvalue, lambda 0, and an infinite limit. So the accumulation point of the eigenvalues lambda of such a system is infinity, and there's a lower bound to the eigenvalues, and there is a smallest eigenvalue, lambda 0. Moreover, the eigenvalues can be put in a countable sequence, so you can arrange them according to their order. The lowest eigenfrequency is, or lowest eigenvalue is lambda 0, the next higher lambda 1, smaller than lambda 2, smaller than lambda 3, and so on up to infinity. So this is a well-ordered scheme of eigenvalues. This is important because in general the eigenfrequencies and the eigenvalues we consider in our systems are by any means not well ordered. They are completely confusing, so there is no ordering scheme for the eigenvalue except for the linear radial wave adiabatic. So that's all, the linear, radial, and adiabatic. Then you have an ordering scheme and a well-ordered scheme of eigenvalues. Okay, this is a very important property. And the second property, which is also remarkable, that the eigenfunction, well, it's formulated a bit misleading. The eigenfunction is, of course, not lambda n, but it's the eigenfunction which belongs to the eigenvalue lambda n, has exactly n zeros in the integration interval. So this is not true for any other problem, but for this problem we have the property that if we look for the eigenfunction of lambda 2, then we will find 2 zeros of this eigenfunction in the integration interval. So if you see the eigenfunction, then you know the order of the eigenvalue. The opposite is not true. If you see the eigenvalue, you don't know which order it has. But if you see the eigenfunctions which belongs to that eigenfrequency or eigenvalue, then you know its order, which is the number, the index n of this eigenvalue and eigenfunction. So you can immediately read off from the eigenfunction. Okay. Well, the third point is you can also show, I haven't shown it here, that the orthonormal system is complete. This is an important additional property. So it's a complete orthonormal system. They are not only orthonormal, and you can expand some function, but you can expand any function. This means completeness. Okay, so this is the third property. So we have in the case of radial linear adiabatic perturbation problem, we have an ordering scheme for eigenvalues and eigenfunction. Lambda 0 and y0 is the so-called fundamental mode. Lambda n and epsilon yn is the nth overtone. And this and the number of zeros of yn indicates the order of the eigenvalue and eigenfunction n. Okay? Keep in mind, this ordering scheme is valid only for radial adiabatic perturbations. Any other adiabatic non-radial doesn't exist. Non-adiabatic, there is no existence in non-adiabatic and in any other system. Despite this fact, people classify modes according to that scheme. Sometimes the scheme of eigenvalues you see remind us of this scheme having a lowest order, first overtone, and so on. But mathematically speaking, this ordering scheme is not present once you deal with another system rather than this radial adiabatic system. It's just reminds you of this ordering scheme, and if you look for the zeros of the eigenfunctions, sometimes it fits, but there are cases where it doesn't fit at all, and if, for instance, modes cross each other, then the ordering system is gone anyway. So keep in mind, even if people address some mode as a P1, P2, P3, or G1, G2, G3, the ordering scheme is not present in the general case. It's only found here, and it's simply that people take this ordering scheme and adopt it for the general case as well. So be careful if in the fully non-adiabatic case someone speaks about the first overtone or the fundamental mode. You have to be very, very critical. This is not necessarily true. So the ordering scheme is only present for a Sturm Liouville problem. Okay, questions? Okay, now we turn to some other property related or which can be proven for self-adjoint and nicely behaved Sturm-Liouville problems, which is the fact that we can deduce our perturbation problem from a variational principle, and the variational principle itself has the advantage that we can derive some integral criteria from the functional formulation of the perturbation problem. Okay, how do we get a variational principle for the eigenvalues, and how can we derive the perturbation from a variational principle? I heard that some of you might be familiar with variational calculus. This is usually done in theoretical mechanics, in classical or analytical mechanics, or in quantum mechanics too. So, but if you don't understand any detail, it will not be critical here. Okay, so what we do to obtain a functional from whose variation we can derive, or which is equivalent then to the perturbation equation, we simply multiply the wave equation with a complex conjugate of zeta and integrate over the volume or over the integration interval. This is the differential operator of the linear adiabatic wave equation multiplied with zeta star, the complex conjugate of zeta, and these are the remaining terms which go with zeta. So this is the modulus of zeta squared times the remaining functions, which is the sigma squared times the function g and the function h. Okay, now same procedure as in any step. We do partial integration of our differential operator here, and we put this derivative to the zeta star by partial integration. Then we have a boundary term, zeta star times gamma adiabatic p times r to the fourth times d zeta by dr between 0 and between the center and the surface of the star. Again, these boundary terms are 0 because p naught is 0 at the outer boundary and r to the fourth is 0 at the inner boundary. Well, minus then the derivative of zeta star times the remaining quantity here. So this is nothing but d zeta by the modulus of d zeta by the r squared, modulus of d zeta by the r squared, which is left here. So this is a nice positive and real quantity which is left, which we achieved simply by partial integration. The rest, of course, is real anyway. Okay, so we can now solve the resulting equation. This equation here we can solve for sigma squared. That's what we do. Okay, so sigma squared times we also take along with sigma squared the dynamical time scale, which is the root of g times the mean density. So this is then a physical quantity, a physical time, because sigma squared was the dimensionless time, and we get, for sigma squared, we get a ratio of 3 integrals. So this is the integral which stands at sigma squared is the zeta modulus of zeta squared times rho times r to the fourth. This goes into the denominator, and these integrals associated with h and the differential operator, they are in the nominator. So we are left with the following expression. This is essentially the function g, which apart from this factor, so we denote it with g tilde here. This is given by density times r to the fourth times the modulus of zeta squared. This is the remaining of the differential operator, and this is the function h times the modulus of the displacement squared. Well, the right-hand side is a so-called functional depending on a function zeta. So sigma squared may be expressed as a functional capital F, which depends, the integrals depend apart, of course, from the stellar model, which enters here through P naught, rho naught, and gamma adiabatic. The right-hand side depends on the function zeta. And now we apply this so-called functional, we apply the variational calculus to this functional zeta. Well, that means we vary the functional zeta with respect to a variation of the function of a so to say arbitrary function zeta. Okay, so we calculate the variation of the functional with respect to variation of the functions zeta. So delta f, this is the variation of this functional f, is given by the variation of the integrals on the right-hand side. So first we have to vary all those places, or we have to apply the variation at all those places where the function zeta is contained. This is, for instance, at the denominator here. We have zeta star times zeta. Well, a variation acts like differentiation, so you have a kind of quotient rule, a kind of product rule, and we apply the product rule with respect to the functional variation of this integral here. So this gives minus 1 over this integral squared times the variation of the integrand. This is g tilde times, well, this is a product, so we apply the product rule. This is delta, the variation of zeta star times zeta, plus zeta star times the variation of zeta. Plus, the next step is then take this and keep this constant and vary the nominator. So it works like a differentiation. So this is plus, keep this part constant and vary these two integrals. So this is the zeta star by the r times d by the r, the variation of zeta, plus the d by the r, and then the next variation will be zeta star will be varied delta zeta star times d zeta by the r. And for this term we have h times delta zeta star, which is the variation of this term, times zeta, the product rule, plus zeta star times the variation of delta zeta. Okay? Now we insert for the quantity for this part divided by one of these integral, we insert the original functional, because the original functional is given by this quantity, and of course, this quantity is given by sigma squared 4 pi g times the mean density. Let's go here. So f of zeta is equal to sigma squared, and this quantity is, so to say, sigma squared times 4 pi g times the mean density. And then we can write at least part of it. The denominator divided by one of these integrals is just sigma squared times 4 pi g times mean density, and we are left then with the following result: delta f. Let's see, then we have a common denominator, which is this part, and we have the following result. Then we can, after some algebra, delta f is 1 over this integral in the denominator times, now we separate according to the variation of delta zeta star and delta zeta. Actually, the expressions are pretty much the same. So what is left on the denominator here is two terms involving either delta zeta star or delta zeta, and the factors which have to be multiplied with this are minus sigma squared times 4 pi g mean density. That comes from inserting for parts of the integrals the functional f of zeta itself, times g tilde times zeta minus d by dr, actually no, f d zeta by dr minus h z. Let's perhaps look to convince you where this comes from. So the sigma squared term, this gives a sigma squared times the g tilde times both delta zeta and delta zeta star, either multiplied with zeta star or zeta. And here we have those terms which are connected with delta zeta. This gives one term which goes with zeta star, or with delta zeta star, this goes with the corresponding term at d by dr, d zeta by dr. So we collect those terms, or we separate or collect those terms which are proportional to delta zeta star and those terms which go with delta zeta. So we end up with the following result. The integral which remains here is delta zeta star times sigma squared g tilde minus the operator, the original differential operator for the linear adiabatic wave equation, minus h zeta. And what we see here, well, we have the complex conjugate of the delta zeta star here, and in the bracketed term it's exactly the same expression, but with the complex conjugate of the function zeta star instead of the original function zeta. So what we have here is some function and its complex conjugate. So the second terms are simply the complex conjugates of the first ones. These are the complex conjugate of this. This is complex conjugate of that. This is complex conjugate of that, and this complex conjugate of that. The sum of a quantity, a complex quantity, and its complex conjugate. What do we get from that? What do we get if we have a complex number and we add add a complex number and its complex conjugate? You are left with a real part of or 2 times, actually it should be 2 times the real part. So what we are left with, apart from factor 2, sorry, the factor 2 is missing, but it doesn't measure. So this should be equal to 2 times the real part of delta zeta star times delta zeta star times the bracketed terms given here. So it's minus sigma squared 4 pi g rho bar times g tilde times zeta minus the differential operator of the adiabatic wave equation minus h times zeta. Now, well, the variation is arbitrary. It's just done to have an arbitrary variation of the function delta zeta or delta zeta star equivalently. So what does it mean? What do we derive from that? So if this is arbitrary, then if we require delta f equals 0, or we are looking for the condition which follows from delta f equal to 0, delta zeta star is arbitrary, then this integral has to vanish. That means if delta zeta star is arbitrary, then the bracketed term has to vanish. And the bracketed term to vanish is, well, this is the differential operator of the linear adiabatic wave equation, and this is the term containing the eigenfrequency and the additional term h zeta. So the vanishing of this bracket is simply our linear adiabatic wave equation. It's identical. If we require this bracketed term to vanish, then this is simply the differential form of the linear adiabatic wave equation. So what we see is either we require the vanishing of this term, which is equivalent to having a solution of the linear adiabatic wave equation, and in this case the variation of our functional vanishes. So the vanishing of the functional is equivalent to having, is equivalent to the differential equation for linear adiabatic radial perturbations. It's okay? Because this variation is arbitrary, so the vanishing of the integral and delta f is equivalent to the vanishing of these bracketed terms. This bracketed terms, vanishing of bracketed terms means this is the linear adiabatic wave equation. So what we found then is the solution of the differential equation for linear radial adiabatic perturbations is equivalent to a local minimum. Delta f equal to 0 means this is a local minimum of the functional with respect to any admissible function zeta. Go back to the f. So delta f equal to 0 means the variation of f vanishes. F was a functional, so this means the minimum of f with respect to the variation of the functions on the right hand side under the integral. Variation of the functional vanishing means we have, this is equivalent to having a solution of the differential wave equation. Okay? It doesn't seem to be too familiar to you. This is a typical approach in analytical mechanics and also in quantum mechanics. Okay, so delta f equal to 0, minimum, local minimum of the functional is equivalent to having the adiabatic wave equation, which is the 0 of this bracketed term. Okay, so once we are looking for eigenvalues, we could also go and see what are the local minima of this functional. And if we have a local minimum of this functional with respect to the to admissible functions zeta, then we have an eigenvalue, because we saw the value of f is simply the eigenvalue itself. F of zeta is sigma squared times 4 pi g rho. but only, of course, in that case if we have a solution of the wave equation on the right-hand side, if f has a local minimum. So we are looking for minimum of the functional, and if we have a minimum, then its value at the minimum will be the eigenfrequency. So this is another approach, an integral approach to determine the solution of a perturbation problem, or to determine the solution of the boundary eigenvalue problem. Okay, so that means solution of the wave equation is equivalent to vanishing variation, here a local minimum of the functional f of theta, and the minima of f of theta correspond to the eigenvalues in the sense that sigma squared times normalization is the minimum or local minimum of f of theta, minimum taken over all admissible functions theta. Okay? How can we use this? Well, it's a lot of mathematics and it's rather counterintuitive going through all these self-adjoint mathematics here, which is hopefully known to you from quantum mechanics. It's exactly the same formalism, and in quantum mechanics you meet or encounter many Sturm-Liouville problems, and therefore this approach should be used, or you can have an exercise for quantum mechanics by going through the analysis here. It's very much the same. Unfortunately, well, it's nice to have therefore I do it in detail, because in general, if we go to non-adiabatic or non-radial problem, the operators do no longer have any properties. So all the operators we are dealing with do not have any properties, but in selected cases, like the radial linear adiabatic case, the operators have a property and have properties, and we can work with these properties. And similar to as in quantum mechanics, the operators are all self-adjoint, have nice properties, and we can use these properties to determine properties of the system, deduce physical consequences from it. This can be done here only for very selected cases, and if we are in the position to do that, then I apologize, I am doing this here. Okay. But we can deduce a very nice and important property or important criterion from this, from the fact that the eigenfrequencies are minima of this functional. Okay, why not looking for the lowest eigenvalue? Well, the lowest eigenvalue, I remind you of the fact that the sigma squares are well ordered. Sigma 0 squared is smaller than sigma 1 squared, than sigma 2 squared. So, and stability or instability in the adiabatic systems can only become, or can only enter through negative values of sigma squared. So once we have an unstable, an adiabatically, radially adiabatic unstable star, how will instability enter the system? Well, if they are well ordered, the instability will in any case be seen by the lowest eigenvalue. If the lowest eigenvalue, if sigma naught squared is smaller than 0, then we have instability. The second, it might be that the second, the sigma 1 is also contributes to instability, but if sigma 1 contributes to instability, then sigma 0 will do in any case. So to determine whether a star is adiabatically unstable, we need to consider the lowest eigenvalue and need to determine whether sigma naught squared is smaller 0 or bigger than 0. If it's bigger than 0, then the star is adiabatically unstable. But if sigma naught squares falls below 0, then we have an adiabatic instability. Well, now we have a procedure to determine the sigma squared as the minimum of the functional. So this might help to determine or give you an upper bound or lower bound for the value of the lowest eigenvalue, because then we have to look or we have to search for the absolute minimum of this quantity on the right hand side, because it's a relative minimum for any of these eigenvalues, and of course it's the absolute minimum if we are looking for the lowest eigenvalue sigma naught squared. Is that clear? Okay. So what we are doing is we would like to use this functional or this variational principle to estimate the lowest eigenfrequency sigma naught or sigma naught squared from this variational principle. So what we know is, well, it's seen here, what we know is that sigma naught squared times 4 pi g times mean density is the absolute minimum of this functional, because it's the lowest eigenvalue and the functional corresponds to the relative minima of this functional. So sigma naught squared is in any case smaller than the minimum of this functional. Now we can put in any function in the functional, and if we get a value for the functional, then the value for some function will be bigger, in any case bigger than its absolute minimum. So if we insert in the functional some function, then the value which we get for this function will be bigger than the minimum of this functional. Okay, do we agree? Putting in or inserting in the functional any function, some crazy function, then it will be bigger than the absolute minimum of that functional. That means we could take as a trial function, we could take constant trial function, zeta equal to constant, insert this, then the value of the functional for constant zeta must be bigger than the lowest eigenfrequency sigma naught squared. Okay? Well, this is a particular simple function, because then in the function all the derivatives of zeta are 0. Okay, let's look at the functional again. If we insert a constant function for the trial function, then the zeta by the r will be 0, so this integral will disappear. And here we have constant zeta, so this gives the modulus of zeta squared, and we have the same value for zeta star times zeta here. So this is just a number here, and because zeta is constant, we can cancel these the modulus of zeta squared here. So what we are left with is then an expression which only involves the function h and g tilde. And the function itself, the zeta has dropped out of the integrals. So what we are left with then is sigma naught squared is smaller than the value of the functional for any value, but it's smaller than f, for instance, for given zeta equal to constant. So what we are left with is the function h, which is left is minus r cubed times the derivative essentially of the pressure and involving the gamma adiabatic divided by the integral over the density times the 4th power of the radius. So we have now an expression for the maximum of sigma naught squared in terms only of quantities of the background model, which is density, pressure, and gamma adiabatic. Well, we are disturbed somewhat by this derivative. So we perform, to get rid of this derivative, we perform a partial integration and put the derivative to the r cubed. Then we have a boundary term. The boundary term involves the pressure and the radius. So at the center of the star, the radius term will make the boundary term 0, and at the surface, the pressure will make the boundary term 0. And then we are left with minus, we have to account for another minus. R cubed gives 3 times r squared times, now the derivative is gone, 3 gamma adiabatic minus 4 times p naught, and we integrate over 4 pi dr, and this is corrected for by the integral down there. The factor 4 pi is inserted for convenience. This is 4 pi r squared rho naught times r squared dr. So this is the upper limit for sigma naught squared. Now we rewrite this in a little bit different way. We define a mean of the adiabatic index by an integral, by the following integral. The mean of the adiabatic index is defined as the volumetric mean of the adiabatic index with a weight function. The weight function is the pressure. So if this is kind of a mean taken over the volume and with a weight function p naught. So the mean adiabatic index is given simply by gamma adiabatic times mean times the weight function over the volume divided by the integral of the weight function over the volume. So this is the definition of gamma adiabatic, and if we define it that way, then we obtain that sigma naught squared is given by, that's how we get rid of this gamma adiabatic under the integral. This is 3 times the mean adiabatic index minus 4 times the ratio of the integral over the weight function divided by the integral over rho naught times r squared. So these are well-defined positive functions or positive integrals, and so the sign of the sigma naught squared, which we are interested in, once we are interested in stability or instability, we are interested in the sign whether sigma naught squared is positive or negative. This sign is not determined by these integrals, they are positive. They are determined by the sign of this bracketed term. So whether sigma naught squared is smaller or bigger than 0 is controlled by the mean of the adiabatic index. Mean means it's the volumetric pressure-weighted mean over the entire star. Okay, in this mean, which part will dominate in determining the mean value of gamma? Well, it's the weight function is the pressure. Where the pressure is high, this domain gets the highest weight. So the surface of the star will not get a high contribution or will not contribute to the mean value too much. It's the center of the star which dominates, and this has to be kept in mind. So if gamma is small at the outer part, this does not mean that the mean value is small as well, because the surface terms or the contribution from the outer envelope and the surface of the star is small in general. Okay, stellar dominates due to the pressure weighting. Okay, let's have a look how this adiabatic index looks like. Well, for the two stellar models we have already seen. This is a 60 solar mass star, and this is the 24 solar mass star. Here is the value of 4/3. Well, I haven't said it explicitly, of course. If the mean adiabatic index falls below 4/3, then the this bracketed terms becomes negative, and then the upper limit for sigma naught squared is negative. So in that case we have negative sigma naught squared and we have instability. So if, let me phrase it once again, if the mean adiabatic index is below 4/3, this term becomes negative, and therefore we have to have negative sigma naught squared, and therefore we have to have instability. Is the opposite true as well? If we have instability, then we have to have mean adiabatic index smaller than 0, smaller than 4/3, just from a logical point of view. Is that true? It is not true. And it's many times, it's in the literature, it's confused, everything. People say, oh, we have instability, it's gamma bit falls below 4. No, no. The mean gamma adiabatic falls below 4/3 is sufficient for instability. It is not the opposite, it's not necessary condition. So it's no necessary condition for stability. The opposite, of course. But keep in mind, it's in this sense, looking at this inequality, which tells you once I have mean adiabatic index below 4/3, then the upper limit to sigma naught squared is negative, and therefore we have to have instability. But the opposite is not true. It's only that direction. Mean adiabatic index below 4/3 means it is sufficient for instability. And that's the way one has to phrase it, because the opposite is not true. Okay. Now let's consider 2 stars. Well, what we see here, the critical value here, once the mean falls below 4/3, then we have instability, and you see here, in particular in the center of the star, the adiabatic index is always more or less well above the critical value. So if you take the mean over the entire star, because that part gets a much higher weight, the domain where gamma falls below 4/3, even in that case, does not count too much, because the weight function is the pressure, and here we are close to the surface. Weight, the pressure is by orders of magnitude smaller than in the center, and so the region where gamma falls below 4/3 does not count too much, or does not have a big influence. In this case, you see there is also, for the 60 solar mass object, there is also a very small domain close to the surface where gamma falls below 4/3, but elsewhere gamma is is well above 4/3, so the mean adiabatic index is not below 4/3 for any of these cases. By the way, which process pushes gamma below 4/3 here? Could you imagine what might be responsible for gamma falling below 4/3 in these 2 stellar models? It's close to it's a process which takes place close to the surface. What might push the adiabatic index below 4/3? It must be a process that takes out energy from the system, because the equation of state becomes softer if you plot, for instance, the log pressure against log density, then you usually have such a behavior. And in these cases, if you pass this, then it becomes flatter. This means the gamma goes, the slope of log p against log rho becomes flatter, and then it goes that way. So this is the domain, or this is how it looks once the gamma falls below 4/3. What might be the reason? So the pressure does not increase that fast as before and after this region or this domain in density. It's a process which takes out energy from the system, which does some reduces the pressure and reduces the energy density and pressure behave in a similar way. It's an ionization process. Well, and here it's the ionization for these two stars. It's the high helium ionization which pushes the adiabatic index below 4/3. So that's the helium ionization for the 60, and this is the helium ionization zone, or the position of the helium ionization zone for the 24 solar mass object. Well, on the basis of such diagrams, people even nowadays decide, well, this star has a region where gamma falls below 4/3. So this is unstable with respect to the criterion that gamma, the mean gamma, should fall below 4/3. Once you take this, take the average of the entire star, you will find it's no longer true. And the argument that in the hydrogen, in the helium ionization zone, you have a value of gamma below 4/3, and this drives the star unstable. This is simply not true. Okay, so be careful if people tell you on the basis of inspection of the adiabatic index alone that the star is unstable with respect to radial adiabatic perturbations. Okay, so keep in mind the stellar core dominates due to the pressure weighting. Okay, so we have a criterion for instability. Well, if the mean adiabatic index falls below 4/3, we have sigma naught squared smaller than 0, and therefore we have instability. So gamma adiabatic, the mean of course, smaller than 4/3 is a sufficient condition for instability. And on the other hand, of course, the opposite, that the mean adiabatic index being bigger than 4/3 is a necessary condition for stability, but not a sufficient one. And people confuse sufficient and necessary. Often the terms sufficient and necessary are confused. So be careful once you read papers on that. Okay. Once the mean adiabatic index is above 4/3, you may have stability and instability, and in that case you actually have to determine the value of sigma naught squared. There is no way to determine stability other than determining precisely the value of sigma naught squared, either by considering the functional or by integrating or looking for solution of the linear differential adiabatic wave equation. Okay, in that case, it's needed to distinguish between stability and instability. You have to perform really you have to solve the eigenvalue problem and determine sigma naught squared precisely. This is the case once you do not meet any of these conditions. Okay. Keep in mind, this is a global criterion. The average has to be taken over the entire star. You cannot just cut the piece you like and determine the adiabatic index in that region and then say, well, I have values of the adiabatic index in the region, in the ionization zone below 4/3, my star will be unstable. I have to consider also those parts of the star where gamma adiabatic might be above 4/3, and due to the weight function being the pressure, these might dominate the ionization zone. So the criterion is a global criterion, and the integration have to be taken over the entire star. Central regions have the highest weight, and gamma adiabatic below 4/3 in the stellar envelope does not necessarily lead to an instability. Okay, it does not necessarily lead to instability. The fact, the question is, which are the physical effects which can change the critical value for third? Well, there are two effects which may affect this. The critical value is for third. We have so far not only considered gravity and the pressure. There might be effects which change the critical value from 4/3 to somewhere else. And two effects which have been discussed in the literature is that rotation may increase. Rotation gives some support to the star, which goes in the direction of increasing, so to say, the pressure, or to give some more support against gravity. That means then the critical value, it's the other way, the critical value which needs to be undergone is smaller if you have an additional support. Relativistic effect may have the opposite effect. Then the star gets more unstable. This means that the critical value of gamma then becomes bigger than 4/3. Another question related to that is, is this criterion really important for astrophysical situation? That means, is that criterion relevant for a star, or is that relevant within or in some evolutionary stage of a star? Well, the thermodynamical processes which can push down the adiabatic index below 4/3 is ionization, as we saw it, or it's the disintegration of nuclei, which appears at the final phase of a star. And the third process is the pair creation, the creation of electron-positron pairs from photons. Well, and if we keep that in mind, ionization, disintegration, pair creation, they may be processes which push the gamma adiabatic below 4/3 from a thermodynamical point. The question then is, what is the astrophysical relevance of this criterion, and what are the scenarios in which this criterion is relevant or comes into play? You probably all know it. It's the collapse of a star at the end of its life. Remember, the equation of state for a relativistically degenerate electron gas has an adiabatic exponent of exactly 4/3. So this is the marginally stable state. And in that case, the gamma does not fall below 4/3 somewhere at the surface of the star, but it falls below 4/3 at the center of the star. That's where the highest contribution to the mean of the adiabatic index is found. The pressure as a weight function, it enforces, or it substantially enhances the effect or the contribution from the center. So in that case, we have gamma falling below 4/3 in the center of the star. So it's really important. And well, the scenarios are simply the collapse of the cores of massive stars forming supernovae, or the collapse of white dwarfs once they reach the Chandrasekhar limit and gamma is exactly 4/3. Then only a small kick is necessary to lead to the collapse of the object. So the astrophysical relevance, of course, it's the final fate of stars. It's supernova explosions of type 1 and type 2. So it's really an important effect, and it has to do with the most exciting events in the life of a star. I am supposed to finish now. Well, this afternoon we will have only a few remarks on this instability, and then we will switch to nonradial adiabatic perturbations. Thanks. Good afternoon, everybody. Welcome back to adiabatic instabilities and stability. This morning we have considered the linear adiabatic radial wave equation. That means we have considered radially symmetric, spherically symmetric adiabatic perturbations of a star. We have considered the perturbation problem, and in the end we have finally got a criterion for instability with respect to radial adiabatic perturbations, which was expressed in terms of the mean adiabatic index. So once the mean adiabatic index falls below 4/3, we found that there is an instability. Be careful, this needs to be formulated in a very careful. It means that gamma below 4/3 means it's sufficient for instability but not necessary. Okay, so, well, once having this stability criterion, which sounds within the framework of our mathematical derivation rather counterintuitive, what is the physical meaning, or how can we get a physical intuitive picture why it is the adiabatic index and why it is the value of 4/3 below which a star will become unstable, below which a star will then start either to expand or collapse, depending on which situation we actually have. So let's finally introduce some intuitive argument why the critical value of the adiabatic index should be 4/3 for dynamical instability. For this purpose, let's consider again hydrostatic equilibrium. The instability must be of mechanical nature because we have only considered the mechanical equations when we derive the stability criterion. So we have to consider the mechanical equations for getting an intuitive picture why gamma falling below 4/3 means that the star is unstable. Hydrostatic equilibrium in usual way, dp by dm is minus g times mass over the power 4 of the radius. In the usual way we use or estimate this equation, we replace the gradient with respect to mass simply by the ratio of pressure over mass, and we keep the mass constant. And once we keep the mass constant, this means that the pressure scales with the radius to r to minus 4. So if we want to keep our star in equilibrium and we try to compress it, then for keeping it in equilibrium, then the radius or the pressure should scale with radius with r to minus 4. So if we compress it and we want to keep it, want it to stay in equilibrium, then the pressure has to rise like r to minus 4. Now, if we compress or change the volume of our star, then also the thermal pressure will change, and if we have adiabatic changes of state, if the compression or the perturbation is fast enough such that the matter cannot exchange heat with its surroundings, then the pressure will go like the density to the power gamma adiabatic. d log p by d log rho is gamma adiabatic, and if we integrate this relation, then the pressure should go with the density to the power gamma adiabatic. This is derived from the thermal equations. This is mechanical equilibrium, and this is the thermodynamics, which gives us this relation or this dependence of the pressure on density. Now, estimating the density by mass over the volume of the sphere, then we have, keeping again the mass fixed, that the pressure will rise once we have an adiabatic change of state with the radius to the power minus 3 times gamma adiabatic. Now, we can have two situations. Either the pressure rises faster than it would need for keeping it in equilibrium. What happens if the thermal pressure, once we compress our star, and the thermal pressure rises faster than it would need to rise once it is in equilibrium, then it will restore the perturbation. Also the opposite happens if we decompress our star and it falls off faster than R2 minus 4 than needed for equilibrium, then it will have a restoring force. It will turn back to the initial state. If it rises more slowly than R2 minus 4, then it will not be restored, but it will collapse, or in the other direction, then it will expand if it rises more. If it rises faster than 10 to minus 4, if we decompress it. So the condition that it rises faster, with compression it rises faster than R2 minus 4 would mean that 3 gamma adiabatic has to be bigger than 4. And this means for stability, 3 times gamma adiabatic has to be bigger than 4, or gamma adiabatic has to be bigger than 4/3 for stability, and of course the opposite for instability. We have that gamma adiabatic is smaller than 4/3. So we can explain it in an intuitive way simply by considering how the pressure scales with radius in equilibrium and how the pressure scales with radius once we adopt a thermal reaction of the thermal pressure onto our compression or onto our perturbation. Okay? Stability means for compressive perturbation, thermal pressure rises faster than required for equilibrium. This means minus 3 gamma adiabatic has to be smaller than minus 4, or gamma adiabatic has to be bigger than 4/3, and vice versa. Instability is found once the adiabatic index is smaller than 4/3. So this is an intuitive explanation for the criterion we found on using lots of mathematics, using the properties of the perturbation equations, going through an equivalence with a functional principle for the perturbation equations. This is a simple explanation why the critical value for gamma adiabatic should be 4/3. Okay, now we are finished with the radial linear adiabatic perturbation. The next step, of course, would be the non-radial linear adiabatic perturbations. So I would need the next file. So what we are talking for today, for the rest of this lecture, will be non-radial adiabatic perturbations. And to start with, we start at the derivation of the general form of the non-radial perturbation equations, which we have considered, I think it was yesterday, and we have derived the system of linearized version of the momentum equation. This is the first component of the momentum equation we had derived yesterday. The second and third one was taken to be replacing the corresponding terms in the mass conservation equation. So the second equation here is the equation for mass conservation. Already replaced are the theta and phi components of the velocity, and we have already applied the expansion in terms of spherical harmonics. So these are the two equations which are left: the radial component of the momentum equation and the mass conservation equation, already replacing the replacing the derivatives with respect to angles theta and phi, and having performed already the expansion in terms of spherical harmonics. Okay, one equation is left here, which needs to be considered once we consider adiabatic changes of state. This is the perturbed version, or the linearized version of the potential, the Poisson's equation, which gives the Laplace operator acting on the Eulerian perturbation of the potential, and on the right hand side we have the Eulerian perturbation of the density. Again, here we have already taken into account the perturbation or the expansion in terms of spherical harmonics, and the derivatives, the angular derivatives, gives this factor L times L plus 1 in the second half, or in the third term of the Poisson's equation. Okay, thermal equations are not necessary here because we want to deal with adiabatic changes, so we can abandon both the energy conservation equation and the energy transport equations. These are the 4, 1, 2, and this is of course a second order system. So this is the fourth order system governing adiabatic linear non-radial pulsations. Okay, now, well, we have to arrive, what we want to do now, or the aim for this, the first half of this lecture will be to get to the standardized form of the non-radial adiabatic equations, and to arrive at these equations, we replace the Eulerian velocity perturbation by the Lagrangian displacement psi r, of course only the radial component, and the relation between the Eulerian velocity perturbation is given by this equation. The Eulerian velocity perturbation is simply the Eulerian time derivative of the Lagrangian component psi r. Okay, this is one transformation or one assumption we make in order to arrive finally at the standard form of the non-radial adiabatic equations. The second one, of course, is the assumption which is basic to all of what we are saying here. It means that we require adiabatic changes of state. This has been discussed already in connection with radial perturbation, and it means that the Lagrangian variation of temperature relative to the unperturbed value is given by nabla adiabatic times the Lagrangian pressure perturbation divided by the stationary pressure stratification. Okay, now to arrive at the standard form, we first of all express the Lagrangian temperature and pressure perturbation in terms of the Eulerian perturbations. I remind you, we have in the last lecture we have derived the general relations between Lagrangian and Eulerian perturbations, and we apply now these relations to the case delta t, delta p, and relate the Lagrangian perturbation to the Eulerian perturbation. Also, this equation is relating Eulerian velocity perturbation with Lagrangian displacement is given in the general discussion of the relation between Eulerian and Lagrangian perturbations. Okay, so what we arrive with is delta t is t tilde Eulerian temperature perturbation plus the Lagrangian displacement times the gradient or the derivative here with respect to radius of the stationary or the hydrostatic temperature stratification, with a parallel or an analog relation for the Lagrangian pressure perturbation given in terms of the Eulerian pressure perturbation and the Lagrangian displacement and the hydrostatic pressure gradient. Okay, so we may now replace, or we may now take both our condition of adiabatic changes of state and reformulate it in terms of the Eulerian perturbations. And what we see then is there is first of all a relation between the Eulerian perturbations of temperature and pressure, which is pretty similar to that of the Lagrangian ones, but there is an additional term which comes from the Lagrangian displacement times the respective gradients of temperature and pressure. So we obtain T tilde over T naught is nabla adiabatic times P tilde over P naught, parallel to the Lagrangian one, minus now the Lagrangian displacement times an expression which involves both the temperature gradient of the background model and the pressure gradient of the background model. So it's, you see, when considering this, these equations, it is important whether we require the Lagrangian entropy variation to vanish or the Eulerian perturbation of the entropy to vanish. They differ by a term which goes with the gradient of the entropy, or in this case with the gradient of the background temperature and pressure. So this is certainly very much different from this equation because there is an additional term. So one should be careful which type of the perturbations have to be set to zero. Here the correct way would be the Lagrangian, to put the Lagrangian perturbation of the entropy equal to zero, because these two issues are different. Okay. Note that, well, this here, these bracketed terms might now be identified. I will not go into the detail. This might be identified with the gradient of the entropy. We could also have written delta S equal to 0 and then relate the Lagrangian perturbation of the entropy and the Eulerian one, and they differ, of course, with by the Lagrangian displacement and the gradient of the entropy. Maybe I should write down it here somehow. Delta S equal to 0. This means the Lagrangian perturbation of the pressure of the entropy equal to 0 is equal to, now we replace the Lagrangian perturbation by the Eulerian perturbation. This is S tilde plus psi r times ds naught over dr, and therefore we can identify this bracket apart from a factor of the specific heat with the entropy gradient of the hydrostatic model. Okay, then next, in the next step, we will make use of the equation of state in the following form, where the density, the relative Eulerian density perturbation is related to the relative Eulerian pressure and temperature variation. Of course, we have our well-known coefficients alpha and delta appearing in this relation. It's simply based on an equation of state where the density depends on pressure and temperature, or where we choose pressure and temperature as the thermodynamic basis. What shall we do with all these equations? Well, we can now replace the density perturbation by the pressure perturbation and the temperature perturbation, and our condition that we are dealing with adiabatic perturbation. So we can then replace also the temperature variation by pressure variation and the Lagrangian displacement. So we can, by this means, we can get rid of density perturbation and temperature variation. This means in the original equations, well, we are left with, of course, the potential perturbation will still be there. Density will be replaced by pressure perturbation, and temperature will be replaced by pressure perturbation and Lagrangian displacement. So we are left with pressure perturbation and Lagrangian displacement here. Well, here there is nothing to do. In the first equation, the density perturbation will be replaced by the pressure perturbation. So we are left with pressure perturbation, the velocity perturbation, or alternatively the Lagrangian displacement and the potential perturbation. So we have enough equations for the remaining variables which are left after these transformations have been done. Okay, so now we introduce a definition. We introduce the quantity A, which is proportional to the entropy gradient. We saw the entropy gradient is more or less this bracketed term, which appears in the relation between temperature and pressure perturbation. This is this bracket here. This bracket is proportional to the entropy gradient of the hydrostatic model, and we define essentially this bracketed term as a quantity A apart from a factor delta. This is delta coming from the equation of state, and this of course is then also proportional to the entropy gradient of our stationary model. Now we change in this expression, we change the thermodynamic basis from temperature to pressure to density and pressure by means of the equation of state. The relative gradient of the density is expressed by the equation of state in terms of the relative gradient of pressure times the coefficient alpha minus delta times the relative gradient of the temperature. If we do that and insert this for the temperature gradient, that means we replace the temperature gradient by pressure gradients and density gradients and sum up all these terms, then we end up with an expression for the quantity A, which contains the relative density gradient and the relative pressure gradient and a coefficient which goes with minus alpha plus delta times nabla adiabatic. Well, this can be given a more compact form, this quantity. This is, we have already derived this expression in one of the previous slides. The minus alpha plus delta nabla adiabatic is 1 over the adiabatic exponent gamma adiabatic. Okay, so we can rewrite the quantity A by relative gradient of density, relative gradient of pressure, and the adiabatic exponent gamma adiabatic. Keep this in mind, we will use this quantity later on. Well, then we introduce some new variables, some transformation, and we will then end up with the standard formulation of the non-radial linear adiabatic problem given the first time by Ledoux and Walraven. So we introduce a new variable u by multiplying the Lagrangian displacement with r squared, and we introduce a new variable y by dividing the Eulerian pressure perturbation by the hydrostatic density stratification. Then we introduce the gravity using the gravitational potential. There is nothing secret behind it, which is according to hydrostatic equilibrium given by minus 1 over the density times the pressure gradient. So this is introduced here in the notation of Ledoux and Wallraven, and of course we do, as we did every time, we adopt the time separation as proportional to the exponential of I omega t, and omega is our eigenfrequency or our eigenvalue of the problem. Okay, if we do that and adopt this notation, then we end up with the following system of equations. Well, the first one, the y was the pressure. So this is the Ledoux and Wallraven formulation of the momentum equation. The second one is the formulation of the mass conservation according to Ledoux and Wallraven, and the last one is the formulation of the linearized version of Poisson's equation. So we have three variables. We have the y and u as a variable, and we have the potential and its derivative as the new variables. This is the formulation according to Ledoux and Wallraven. Of course, we have to satisfy boundary conditions. At the center, we have the requirement, as usual, that we have regularity. That means here u has to be 0 in the center, and the Eulerian perturbation of the potential has to be 0 there. And at the boundary, we have, first of all, the condition that the boundary should be force-free. They are not unambiguous, of course, as discussed already before, but the correct version of the boundary condition is setting the Lagrangian pressure perturbation equal to 0. This does not mean that the Eulerian perturbation is 0, but we have to correct somewhat the Eulerian pressure perturbation to give an expression which is equivalent to the Lagrangian pressure perturbation to be 0. So Eulerian pressure perturbation plus displacement times the gradient of pressure has to be 0. This is the force-free condition, and the second condition is similar to that which we applied for the full system. Well, there should be a continuity of the potential to the vacuum solution of the potential, and this continuity, this continuous connection with the vacuum solution, this provides an additional boundary condition for the potential. So we have 4 boundary conditions, again, 2 at the center, 2 at the surface, and we end up with a fourth order linear non-radial perturbation problem. Well, comparing these equations now with the radial adiabatic problem, of course, it's fourth order due to the gravitational potential. This is known. And as in the radial case, if we look for the coefficients which appear in our equation, there are the same, first of all, the same quantities. It's the pressure stratification, it's the density stratification, and it is the adiabatic exponent or coefficient gamma adiabatic. What we observe in addition to the radial case, of course, is the factor L times L plus 1. That's clear. That must appear because this is, we have non-spherical perturbations, but this is also the appearance of this quantity A and the gravity G. So if we look at the perturbation equation, we have the gravity here appearing and the expression or the definition of A. So G and A, this is new compared to the radial case, and we have also terms which go with L times L plus 1. This is the difference between the radial and the non-radial adiabatic perturbation equations. Okay. Now, I should perhaps mention here, the Ledoux-Walraven formulation is one of the standard formulation of the adiabatic non-radial problem. There are also alternatives. There may be many alternatives, but one of the alternatives which is quoted very often is the Dzymbowski variables. It's just a different transformation of the system of equations. It does not change anything. It's just another representation of this equation in terms of different dependent variables, which might be more convenient in certain circumstances. So the Dzymbowski variables, well, Dzymbowski has introduced 4 variables, y1 to y4. The y1 is essentially the Lagrangian displacement. The y2 is something like the second variables of Ledoux and Walraven. I remind you, p tilde over rho naught was essentially the Ledoux-Walraven variable. He adds another term by using the potential, the Eulerian variation of the potential. Well, and y3 and y4 are essentially the potential, the Eulerian perturbation of the potential, and the gradient of the Eulerian perturbation of the potential. All these are normalized here by 1 over the gravity. Then he introduces some new combinations of the background coefficients. So the background model is described here in terms of a coefficient C1, which essentially describes the stratification of mass, and then U is also describing somewhat the distribution or the stratification of mass, whereas the coefficient V describes essentially the pressure gradient or the logarithmic derivative of the pressure gradient. And he uses another a slightly different variation or slightly different dimensionless frequency sigma. It's given by omega squared over the density. Well, it's essentially the normalization by the dynamical timescale, but it involves another numerical factor. So there's not much difference. And once we adopt this notation, then we end up with 4 equations, with a system of 4 first-order equations, which is given here. So on the left-hand side, we have r times dy1 to y4 by dr, and on the right-hand side, we have a linear combination of the dependent variables with the coefficients u, v, c1, a, and so on. So this is another other representation which many people have used and many people are still using for the description of the non-radial adiabatic linear problem. Okay, we will keep to the Ledoux and Walraven formulation in the following. Just for completeness, I wanted to show that this is an alternative representation of the Ledoux and Walraven scheme. Now, first of all, let's consider Poisson's equation. This might be written in terms of second derivative of potential plus first derivative of the potential with respect to radius, plus a term that goes like L times L plus 1 over R squared of the Eulerian potential is of the order, or is given by 4 pi g times the Eulerian density perturbation. Now, if we estimate these terms to order of magnitude, then we will end up, if we express phi tilde, the Eulerian potential perturbation, then we will find that phi tilde should be of the order of 1 over L times L plus 1, and the order of the density perturbation, the second derivative of the potential variation, and the first derivative of the potential. So the potential itself will be of the order of 1 over L times L plus 1. So this means if L goes to infinity, well, the potential will become small. Small compared, for instance, with the density perturbation. And the Cowling's so-called Cowling approximation consists of neglecting the potential at all. So this estimate should give a reason or an argument when we can neglect the Eulerian potential perturbation as compared, for instance, with a density perturbation. This will be true for high values of L. An intuitive argument will be, well, if we have many nodes on our surface, then the potential, so to say, will average out the additional gravitational forces. Another situation where we can neglect the potential would be that the gravitational field is dominated by a core, and the pulsation will take place only in the envelope of the star. Then the small density variations we have in the envelope will produce only very small changes to the gravitational force, and therefore in that case we may also neglect the changes of force due to small density variations in the envelope. So, but one argument is if we go to large values of the harmonic degree, then we may neglect the gravitational potential. This is not true if we have low values of L, in particular for the spherical symmetric case, but we have no problem with the spherical symmetric case because in that case we have already integrated the potential and we have written it in an algebraic form, and so we don't need to consider the potential and the Poisson's equation separately as in the case of non-radial pulsations. So a quite common approximation in non-radial, considering non-radial perturbation, is so-called Cowling's approximation. We neglect the potential and its derivative completely. This has the advantage that the order of the system reduces from 4 to 2, and we end up with an equation which is at least mathematically comparable to the equation for radial adiabatic perturbations. Okay? So small scale azimuthal perturbations will average out, and phi tilde may be neglected for large L, and this is the content of Cowling's approximation. Actually, there is not the Cowling approximation does not make a big physical difference because it's simply a quantitative change of frequency which might be seen, but not a qualitative change. It is physically, it does not introduce any severe approximation, and also it does not lead to substantial to very big changes in the spectrum of the star. Once you are interested, of course, in very precise measurements, then you should, at least for low harmonic degree pulsation, then you should, just for accuracy, you should not apply Cowling's approximation. Okay, the consequence is, the nice consequence, we will have less work because the order of the differential system is then reduced to second order. Okay, now coming back to the Ledoux and Wallraven formulation of our non-radial adiabatic system. We introduce, for simplicity or for convenience, we introduce from the variables u and v, u and y, we introduce new variables v and w by multiplying them by an exponential of the integral rho 0 g over gamma adiabatic p, and for the variable y and w we introduce an exponential or multiply it with an exponential of the integral over our quantity a dr. Why do we do this? Let's go back to the equations. Well, of course, we now adopt also the Cowling's approximation, so we get rid of all these potentials, we get rid of the entire equation, and we get rid of the two terms here in the uppermost two equations. So what are we doing? Well, this reminds you of the integral over the integral which is appearing in the exponential in the transformation. So this is some kind of a diagonal term, and here is a diagonal term here which includes the coefficient a. To remind you, we had done a transformation exponential to integral over a dr. So these are the, so to say, the diagonal terms here. It looks as if they are anti-diagonal, but they are the diagonal terms. This is u, and this is u, and this y. The aim of the transformation is to get rid of these diagonal terms, and this is actually explicitly done by the transformation, including the exponentials of the integral over the coefficients of the diagonal terms. You can convince yourself that if you do this, if you go to the new variables v and w, then these diagonal terms will disappear. Okay. Well, the transformation eliminates the diagonal terms on the right-hand side of the differential equation, and we are then finally left, together with Cowling's approximation, we are left with the two differential equations. dw by dr is sigma squared times the mean density plus the term, the expression Ga divided by r squared times v times the exponential expression here, and the difference of these two integrals. And on the other side we have dv by dr is the bracketed term involving L times L plus 1 over sigma squared, and here we have essentially the sound speed squared times w times this exponential, and observe the exponential here is just the inverse of the exponential in the second equation. They're just the inverse of each other. Omega squared is sigma squared times 4 pi g times the mean density. Okay, why did we do this? Well, we are now going to perform a so-called local analysis. What is a local analysis of a differential equation? Well, the local analysis consists of regarding the coefficients of the differential equation to be constant. What do we achieve by that? If we consider the coefficients of a differential equation, well, all the coefficients of our differential equation depend on the background model, or in other words, on the radial coordinate or on the mass coordinate. So they are not constant, and it's not easy to get a solution for that. But if you take or consider the coefficients to be constant, then linear differential equation with constant coefficients has exponentials as their solutions. In that case, we can adopt the solution of the form exponential of ikr, where k is some kind of wave number or 1 over the wavelength. So if we formally consider the coefficients of the differential equations to be constant, which is actually not true, then we can write the solution of the form exponential of ik times r. The question is, under which condition could we consider the coefficients to be constant? What might be a justification to keep the coefficients constant and look for solutions of the form of an exponential? What might be an argument? Well, consider this is the variation, for instance, of pressure P naught as a function of R, has some behavior like that, has a certain variation, scale of variation, certain pressure scale height. What might be a justification to consider this as a constant, or perhaps locally as a constant? Well, we take a small region here and we compare it with the scale or the typical variation scale of our waves we are considering. Well, this describes a wave. If the wave number is very high, it means that the wavelength over which the typical quantities within the wave change rapidly. If this k is large compared to the variation of the background, then this might or could be a reasonable assumption. So what we are looking here essentially, or this approximation tends to consider small wavelengths or small wavelengths, short wavelengths, high variations within the wave compared to the background, compared to, for instance, the variation of pressure compared with that of the wave. Okay, so this might be justified by the assumption or by considering the variations of the solutions, namely the wave, to be faster than that of the coefficient, that means of the background quantities. In these cases, if we do that, then we might have a reasonable solution. That means sufficiently short wavelengths are considered. Well, what we cannot do once we do this approximation, we cannot impose boundary conditions, because, well, we lose the boundary conditions by this assumption of a solution in the form exponential of IKR. We would have to impose on this exponential of IKR, we would have to impose a boundary condition at the very center, at the very surface. Of course, when it's going from the very center to the very surface, then the condition that the variation of the solution is much faster than that of the background is no longer valid. So we cannot impose boundary conditions there, and that means we do not solve boundary eigenvalue problems, and in particular we do not expect to get a discrete spectrum for our modes. So this assumption also also tells us we cannot impose boundary conditions, and we do not consider a discrete spectrum as in the solution of the full problem, because on the basis of this local analysis we cannot impose boundary conditions and therefore do not get discrete eigenvalues and eigenfunctions. This is the characteristics of a local analysis, but rather we have we consider solutions of the form exponential of IKR, and let's see if we assume solutions of this type, what we'll get as a result. Okay, so we take this assumption: solutions are proportional to IKR, and with that and consider at least locally the background quantities to be constant, and let's see what we get for the wave number k. Well, doing that, we replace the derivative with respect to radius of w and k with a multiplication with ik. This is simply taking the exponential ikr, and of course this exponential then can be cancelled from the equations, and we are left with an algebraic equation for W, V, W, and the rest of our coefficients. Now I would like to remind you that these two exponential are just the inverse of each other, and what we are doing now is we insert the V, or we insert the value for V in the upper equation, multiply the whole thing with ik, and then after some elementary algebra, these two exponentials cancel because they are the inverse of each other. On the left hand side we are left with minus k squared times W is the first expression here times the expression appearing here times W. Anything else cancels. Well, also of course the W itself cancels, and we end up with a relation between the wave number k and the other remaining coefficients. Well, it is a relation between k, and in particular on the right hand side we have the frequency sigma on two places. Sigma appears here, and also the eigenfrequency appears here. The other coefficients are formally kept or formally regarded as constants, and we will see in a moment how we can interpret this relation. So in the end we get a relation between wave number and frequency. This is called, we have already seen such relations, this is usually called a dispersion relation. Dispersion relation between wave number and frequency and the other parameters of the system. The dispersion relation depends on the other parameters of the system as well. This may be read in two ways. Either we consider this equation as an equation for the wave number k for given frequency, or we can also invert this and say, well, this is an equation for the frequency for given wave number k. We will consider this dispersion relation, this local dispersion relation, in both ways, considering it either as an equation for wave number for given frequency, or as an equation for the frequencies for given wave numbers. Can be read in both ways. Okay, of course we will hence in the following we will omit the subscript 0 to make the formula a little bit less crowded and less confusing. Okay, so we have dispersion relation which may be read either as a function k of sigma or sigma of k. Of course it also depends as a parameter the harmonic degree L, and because all these quantities depend on radius, also this dispersion relation depends also on the radial position we consider. P0 and ρ0 are functions of the hydrostatic model, and therefore the coefficients or this dispersion relation in general depends on radius, the parameter L, and on sigma, or vice versa. Sigma of k, L, R can read it also the opposite way. Now we have to distinguish according to whether the wave number is real or imaginary. We have a quadratic equation for k. If we prescribe the right hand side, then we can solve it for k. Well, the right hand side might be positive or negative, so we have as a root of the positive or negative value of the right hand side, k might be real or it might be imaginary, depending on whether the right hand side gives us a positive or a negative sign. Once k is real, we have we have an exponential of IKR. If K is real, this describes oscillatory waves, and this is called an oscillatory solution. If K is imaginary, then we have exponential. We do no longer have an oscillatory behavior, but we have an exponential behavior, so exponentially decreasing or increasing solution. In that case, we are talking about so-called evanescent solutions. This means distinguishes between real and imaginary values of the wave numbers. Keep in mind, K real means oscillatory solution, K imaginary is equivalent to an exponential, or in other words, evanescent solution. Okay, so this is the same dispersion relation, simply cutting out the W and somewhat rearranging this dispersion relation. In particularly, we have multiplied it with -1. We have taken out of the integral the factor minus GA, and we have taken out of the integral the value gamma adiabatic P over rho, taking out this out of the bracketed terms, and we end up with it's just a little bit of algebra which has to be which is applied with this dispersion relation, and we are left with this form for the local dispersion relation for radial adiabatic, for non-radial adiabatic perturbations. Well, there are two quantities appearing here which are new and which are given a new name, or which are defined in a new way. This is the factor minus gravity times the quantity A. I would remind you, the A was proportional to the entropy gradient within our hydrostatic background model. This has the dimensions of a frequency squared, and it's according to its discoverer, it's called the Brunt Väisälä frequency. He was a Finnish guy, so it's pretty difficult to pronounce Väisälä. So it's I don't know whether I'm right. We call it Brunt Väisälä frequency. Okay. So this is a new frequency appearing here, Brunt Väisälä frequency, and the second frequency appearing here, or second quantity which appears here, which also has the dimension of a frequency, is the so-called lamp frequency. This is the frequency which appears here. It's gamma adiabatic times P over rho. We know this guy already. This is the sound speed squared. Sound speed squared divided by radius squared is a frequency squared times L plus 1. This is defined, or is called, the so-called lamp frequency. So we have in our dispersion relation, we have the lamp frequency here. So this is the ratio. What we have here is the ratio of lamp frequency over the frequency we consider, and this here is the ratio of frequency over the Brunt Väisälä frequency, which appears in the first bracketed term. Okay, so that's for the definition we use. Well, I already said gamma adiabatic times P over rho is simply the sound speed squared. Okay, now, well, what is the physical interpretation? Okay, once we can perform two approximations to this dispersion relation. First of all, we put the terms GA equal to 0. What does it mean? We put either the gravity equal to 0 or the quantity A equal to 0. A was the entropy gradient. So what we are doing is we neglect the entropy gradient here. So if we put artificially GA equal to 0, what happens to our to our dispersion relation. Well, we have to multiply this in there, and then we are left with sigma squared times p over rho, and then we are essentially left with, so only one term is left here, and this frequency might be multiplied into this bracket. Then we have the Brunt-Väisälä frequency minus the frequency. So we end up with another dispersion relation, which looks simpler, which is sigma squared minus Brunt-Väisälä frequency squared 1 over sound speed squared is equal to k squared. Now solve that for the frequency. If we solve this for the frequency, then we see frequency is sound speed squared times k squared plus, well, the lamp frequency contains the factor L times L plus 1, L times L plus 1 over R squared. So the frequency is given by sound speed squared times wave number squared. This L times L plus 1 is some kind of azimuthal wave number, so this is proportional to L squared. This is the dispersion relation for sound waves. This is the local description, or is a local version of the description or the relation between wave number and frequency for a sound wave. Okay, this is so-called dispersion relation for sound waves. I have to finish here. I have to stop here. Perhaps I can just start a little bit. We can also do the opposite. We can, rather than asking for zero entropy gradient, we can exclude sound waves by putting sound speed to infinity. And if we do this, then if we put sound speed to infinity, then sound speed to infinity means we have to multiply this in here, and then this term 1 over sound speed squared will drop out, and we will be left with essentially the left bracket, and this bracket can then be written as k squared is Brunt-Väisälä frequency minus sigma squared times L plus 1 over 1 over sigma squared. If we rewrite sigma squared in terms of omega squared, then we are left with omega squared. If we solve it now for sigma or omega squared, then we have this relation reduces to Brunt-Väisälä frequency squared divided by 1 plus k squared over L times L plus 1 times R squared over R squared. This means this is the radial wave number over the tangential wave number squared. And the frequency by which we have the frequency wave number relation is a typical frequency wave number relation for the so-called gravity modes. The gravity modes live from Brunt-Väisälä frequency, which is gravity and entropy gradient. Okay, so we end up in these two limiting cases. Once we exclude either the gravity waves or we exclude sound waves, then we end up either with the dispersion relation for sound waves or the dispersion relation for gravity waves. Okay, let's stop here, and we will continue on this subject then tomorrow.